In this part of the lecture, we will learn how to use a jumping link instruction to do an unconditional jump in RISC-V. So if I look at this code that I have, the C code that I have in the picture, I have a function foo that does a call to a function bar. And let's say that this is the function bar. At some point in the execution of the function bar, we'll be executing a return statement. And this return statement has to know the address that it has to return to. Therefore, when I do the call at this point in function bar, when making this call, I must remember the address of the instruction that comes immediately after the call, so that when I'm executing the return statement, I know where I am returning to. The way to do that in RISC-V assembly is to use the jump and link instruction, JAL, and typically I would be specifying array, which is the return address register, to the jump and link instruction so that the value of the return address is saved into array for future use. However, in this part of the lecture, we're going to learn a different use, which is a very clever use actually in the design of the RISC-V architecture for the jump and link instruction. To understand that, first we need to talk about the constant 0. The constant 0 is the register 0 in the RISC-V processor. It's a hardwired register that cannot be overwritten and always will contain the number 0. So it has several common uses. For example, if you want to move a value between two registers to make a copy from one register to another, you can simply add the register 0 to the source register, and that will copy its value into the destination register in using an add operation. You can use the register 0 also to set a variable to 0. For example, by adding 0 to 0, you end up writing 0 in the register S4. And you can use this also to do an unconditional jump. And there are two ways that you can do the unconditional jump. You can use the register 0 in a branch equal instruction, where you test whether 0 is equal 0. That will always be true, and that will be an unconditional branch instruction. Or you can do an unconditional jump instruction, where you specify that the return address is to be written into the register 0 instead of array. That way, the return address will be discarded, and the instruction will actually be perform an unconditional jump from where you cannot return. All these are different uses of the register 0. So now that we have understood how we can use the jump and link instruction as an unconditional jump instruction, let's look at the UJ type format in RISC-V. In this piece of code, I have a jump and link where the target has been specified to be register 0. And sorry, not the target, but the return address is register 0 and the target is exit. And if I look at the distance between the jump and link instruction and the exit, I will see that the distance is 8. I'm jumping over one instruction, so I'm doing a jump that is 2 instructions in length, which is 8 bits. Each instruction, which is 8, which each instruction has 4 bytes. We can now look at the effect of the jump and link instruction. What the jump and link instruction will do is to write the value of PC plus 4 in the destination register. In this case, I specified the destination register 0, so we're going to be writing to the register 0. And then it will also change the value of the program counter to be the value of the current program counter plus the immediate value, where the 0 bit of the immediate value is always assumed to be 0. It's not specified in the instruction. As you notice in the screen, the immediate value for the UJ type is quite shuffled. The position of the bits is quite shuffled into the instruction. So for this example, this will be the specification for the immediate value. And the opcode for the jump and link instruction is 6F, and I specify that the destination register is register 0. So this would be the binary representation for the jump and link instruction, and in memory I will see this hexadecimal word. So first, let's take a look at saving the return address. What the jump and link instruction does, it takes the value, the current value of the PC, adds 4 to it to obtain the value of PC plus 4, and then writes the result of this addition into the specified destination register. But in this case, I specify the register 0 as the destination register. The value of the register 0 can never change. Therefore, the value PC plus 4 that was just computed will be discarded because it's not needed for an unconditional jump instruction. I know that may seem a bit complex to specify a register and to use the jump and link instruction to do an unconditional jump, but actually it's a very clever design compared, for example, the MIPS architecture, because you don't need an extra instruction that will be the unconditional jump instruction. So the next part that we need to look at is how do you calculate the immediate for the jump. In this case, as we need to jump 8 bytes because the immediate value would then be 8. And the first thing that we need to do is to express 8 in 21 signed 21-bit signed form, and this is how 8 looks like when I express with 21 bits. Now I will decompose these 20 bits in the fields for the immediate specified in the instruction. So I have the bits 12 to 19 that appears in the lower part of the immediate. I have then the bit 11, and then I have the bits 1 to 10. The most significant bit of the immediate is the most significant bit of the jump and link instruction, and that's very convenient because if I want to check whether the immediate is negative, all I have to do is to check the most significant bit of the binary representation of the instruction. And finally, the bit 0 of the immediate is implicit. It does not need to be represented in the instruction, and that is because you can never jump to an odd address. You can only jump to even addresses in RISC-V. Now, if I sign extend the immediate to 32 bits, that would be the binary representation. If I use the hexadecimal representation to make my calculation easier here on this slide, I can then add the value of the PC of the jump and link instruction to it. And what that will give me is the new value of the PC after the execution of the jump and link instruction. So in this case, when I reach the instruction at the address 1000.008, I will immediately, the next instruction that I'm going to execute is the instruction at the address 1000.0010, skipping over the instruction at 1000.00C. So we have seen several different specifications of immediates in the different types of instructions in this lecture. And the RISC-V manual will have significant text and quite a bit of complexity is explaining how these types are converted into the immediates. What I try to do in this animation here is to try to illustrate how the hardware converts that immediate value that appears in the type into the immediate value that it has to use for the calculation instruction. So we start with the I type, that is, for example, for the add I instruction. To convert the immediate value from the type into the 32-bit immediate value, all that the hardware has to do is to shift the lower bits to the right and thus sign extending the value. For the S type, the immediate value appears split into the instruction in this shape, and to obtain the 32-bit S immediate value, all the hardware has to do is to shift the values to the right. For the B type, that's the type for the branch instruction, the conversion into the immediate value is slightly more complex, but again is only shifts to the right of the different portion. Actually, there is one shift to the left of the original bit 7, and then that portion shifts into place, the value sign extended, and you add 0 into the least significant bit because there is the implicit 0 bit. Notice that although I'm showing those shifts sequentially here so that you can see what's going on in the hardware, they can all happen in parallel. For the U type, that immediate value that appears in the instruction is converted into the 32-bit immediate value by simply adding zeros to the lower part of the word. For the J type, the type that we just studied in this part of the lecture, the conversion between that immediate value and the 32-bit values that we need starts with the shift to the right, that bit field that I just shown. There's the single bit that is the bit 11 that has to be shifted into place. Then the value sign extended, and I added the implicit 0 that is in the instruction to the immediate value. So I hope that this animation helps you get a sense that this, what appears to be a fairly complex way to specify the immediate value was done very carefully by the designers of RISC-V in order to facilitate the generation of the immediate value by the hardware. So if we do a recap now of what we have learned in this part of the lecture, we have seen how to use the jump and link instruction as an unconditional jump instruction. And we have seen that the labels that appear into the assembly code do not appear in the binary representation of the program. They are translated into the immediate values of instructions. We recall that the immediate value of the jump instruction has an implicit bit 0 because you can only jump to even addresses. So in an even address, the lowest bit is always 0. It's a 21-bit immediate. The immediate is sign extended. Therefore, it is possible to do a jump backwards. And I can tell whether a jump is forward or backwards by simply examining the most significant bit of the instruction, which is the most significant bit of the immediate value. And finally, we have seen that the specification of the immediate values in the binary representation of RISC-V is hardware-oriented in the sense that they were specified in that way to facilitate the implementation of the conversion of the immediate fields in the types to the immediate values that are needed by the processor for the execution of the instructions.